Alright, let's get started. Hi, my name is Tim McDonald. This is our Physics 2 project number 2. I am here with Dane and Adrian, and we're going to be talking about buoyancy force. Okay, to start things off, what is a buoyancy force? Well, a buoyancy force is a force caused by the difference in pressures on an object that is in a liquid. For example, let's say you throw a piece of wood into a body of water. The piece of wood is going to want to float. And the buoyancy force is what causes that piece of wood to float. And with that piece of knowledge, there must be a way to calculate said buoyancy force. And the easiest way to do that is with the Archimedes principle, which says the buoyancy force is equal to the weight of the displaced liquid, which is basically just the volume of the liquid displaced times its density. Now let's get into how buoyancy is similar to things that we've already covered in class. It uses a lot of the same quantities like gravity, volume, and density, which we've already covered in last term and this term. It goes over forces in motion with what we studied a lot last term with forces in motion involving the study of forces. Buoyancy force, well, in the name, force, automatically going to be similar. And it's also similar to the Newton law. It relates in the same way with the studies of mechanics and how things move around. It's all encompassed in that. And then with some key differences. We haven't gone over pressure at all, and one big thing with this, we haven't really gone over liquid mechanics at all. This is completely new with water and how it acts and reacts with certain situations, and even the Archimedes principle with weight. We haven't covered much of that. That's really big and different.
Thanks, Tim, for describing the buoyant force and showing us the similarities and differences from what we have learned in the past in our physics classes. I'm going to continue that by showing us our current models for our physics motions. We have our model from 211, which is mostly translational motion, as well as forces, energy, and momentum. And in 212, we've developed some angular motion, which includes angular momentum and all other position, velocity, and acceleration values at an angle. From these models, we can build our buoyant force. The variables we'll be using to build our buoyant force are force in newtons, pressure newtons per meter squared, area in meters squared, fluid density in kilograms per meter cubed, acceleration due to gravity in meters per second squared, the height beneath our liquid surface in meters, the height of our object in meters, and volume in meters cubed. From looking at the picture on the right, see there's a pressure on the top and there's a pressure on the bottom. These two pressures create an upward force and a downward force. Subtracting the downward force from the upward force, you get our buoyant force. Now let's simplify this. Pressure is equal to force divided by area. And now breaking that down to classify the force on the top and the bottom, we have the force down, the pressure on the top times the area of the top. And the force upwards is the pressure on the bottom times the area of the bottom. Plugging these into our buoyant force equation, we have pressure on the bottom times area minus pressure on the top times area. Hydrostatic gauge pressure can be represented as fluid density times the acceleration due to gravity times the height beneath the liquid surface. Now finding the pressure for each top and bottom of the can, we have the pressure on the top is equal to the fluid density times gravity times the height from the surface to the top of the can. For the pressure on the bottom, we have fluid density times gravity times the height to the bottom of the can. Plugging these all in, we get fluid density times gravity times height to the bottom times area minus fluid density times gravity times height to the top times area, equaling our buoyant force. Some factoring, you can take out our like terms, and we have fluid density times gravity times area. And in parentheses, we have the height to the bottom minus the height to the top. Some critical thinking, as well as looking at that picture on the bottom right, we can see that the height to the bottom minus the height to the top is simply equal to the height of the can. We also know that the area of a surface times the height of a surface is equal to the volume of the surface. Plugging this all back into our buoyant force equation, we have fluid density times gravity times the volume. The volume is of the fluid, not of the can. They can be different, and in our case, we need the volume of the fluid.
Thanks, Adrian, for demonstrating how we solved for our model. In order to make sure that our model is accurate to real-world phenomena requires a similar sense-making process to what we have done for real-world context problems. First, the most straightforward way to check our model is to check the units. When we plug in SI units, they solve for the appropriate quantity. In this case, we are solving for a force, so we should get units of newtons when we plug in SI units. And when we do so, we do end up with newtons. So in this way, our model is correct. In addition, we need to make sure that trends in the model are true with what we expect to see from a physical standpoint. By holding all variables constant and varying one, we can make sure that the expected result of changing that single variable is represented in the equation. For our first case, we are looking at changing the volume of the shape. So if we increase the volume of the shape, we would expect that because more of the fluid is displaced, the buoyant force will, as a result, increase as the volume of the shape increases. Using the density of water and near-Earth surface gravity in SI units, we generated the graph on the right and found that the trend does keep in line with what we expect physically, where greater buoyant forces result from greater volumes of the shape in the fluid. Now looking at another variable, in this case the density of fluid, we expect that when the fluid is more dense, there would be more particles or masses of particles in contact with the object per unit of area. So because more contact is being made, the buoyant force would be expected to increase. You can also think of this as being a comparison of a more dense fluid compared to a less dense fluid. A more dense fluid will be more difficult to infiltrate. The buoyant force is stronger on that fluid than a less dense fluid. A less dense fluid will let objects into it more easily. Using this, a volume of 100 cubic meters, and the same gravity as before, we see that the graph below shows that the model is also true for this case. Looking at the final variable, gravity, when gravity is increased, we expect that the force of gravity on the object would also increase. As a result, the fluid should, through either compression or resistance, exert a stronger force back on the object due to the increased gravitational force. We can almost compare this to the interaction between normal forces and gravitational forces, although the object is not necessarily always at rest. It sometimes will move up or down. We'll get into those special cases later. Using the values for density and volume before, we can generate a graph that shows the expected trend below. And based on these three sense-making strategies, we can say that our model does accurately describe the buoyant force. There are some special cases involving objects that either float or sink in a fluid. When an object's force of gravity, which is dependent on its mass and gravitational force, is greater than that of the buoyant force, it of course will sink, it will accelerate downward. This case is shown by the force diagram on the left, labeled with an uppercase A. And in contrast, when the buoyant force is greater than the force of gravity, the object will float on the surface instead, the surface of the fluid that being. And this case is shown in case B, where, as shown by the force diagram, it accelerates upward. Building off of these special cases, Adrian will now explore some real-world context examples where this model can be applied.
Thanks, Dane, for making sense of this model. I'm going to be finding some real-world scenarios and breaking them down in terms of our model. First one is a little rock being dropped into H2O. In this case, the rock has some mass, fairly small, and then some acceleration due to gravity, which creates a force. In this case, our buoyant force is not powerful enough to hold the rock in a vertical state in the water. It simply sinks because the force that it has coming into the water is greater than the buoyant force. And anytime this happens, the object will sink. Another example is an aircraft carrier, an object with much more mass than the little rock, but it seems to float nicely on top of the water, whereas the rock does not. It's because the density of the aircraft carrier is less than the density of the water below it. This also means that the force of the object is less than the buoyant force, so much to the point where the buoyant force brings the object, or doesn't even let the object go beneath the liquid. There is some part of the aircraft carrier, though, that is beneath the surface, and that is simply because of its mass and some denser parts of it that can outweigh the liquid. We use one reference for this project. It was a Khan Academy article on the buoyant force. Very helpful, very informative. Highly recommend the read. Thank you guys so much for listening to our presentation.